Today, you will be able to evaluate the limit of a function using the direct substitution method. This is Chapter 1, Section 3. We call this in calculus evaluating limits analytically. What they mean by the direct substitution method is exactly what you learned in Algebra 1 when you tried to find a y value. Remember, to find a y value, you simply plug in the given x value. Since a limit is simply the y value when you get some x value, then to find the limit, you just plug in whatever number c is into the function and evaluate normally. Notice here though it says it must be continuous. This means that the x value, whatever it is, whatever c is, cannot create a hole or a vertical asymptote. If those two things occur, then you will have to wait for another lesson in order to figure out how to evaluate a limit there. Let's look at the very first example. Example 1. Find the limit as x approaches 0 of x squared plus 2x minus 8 over 2 times x minus 2. The first question is this function continuous at x equals 0? So if we were to plug 0 into the function, would it create a hole? Would it create a vertical asymptote? Vertical asymptotes are created when the bottom is 0. So when I plug 0 in here, I get 2 times negative 2. That's allowed, no problem. If I factored this out right here, I would have x plus 4 and x minus 2. These two things cancel, but notice that the hole is at x equals 2. We're not interested in x equals 2, we're interested in x equals 0. So yes, at x equals 0, the function is continuous, thus we can take this c value, the 0, and plug it in for every x we see. So the limit as x approaches 0 becomes 0 squared plus 2 times 0 minus 8 over 2 times 0 minus 2. Simplify this problem to negative 8 over negative 4, which you should know as a positive 2. So the limit as x approaches 0 for this function is 2. There are several properties of limits that you need to have memorized. I'm going to put them up here slowly. First are the basics. The limit of x as x approaches c, the limit as x approaches some number of b, where b is just another number. Well, since you can't plug a number in for a number, you can only plug a number in for a variable, this limit is simply going to be b. This is like if you see a graph where y equals 3. No matter what x value you get close to on this graph, the y value is always the exact same number. Another basics, the limit as x approaches c is just going to be c, because if you plug that directly in for x, then x is just going to become c. Third basic, the limit as x approaches c of x to some power n. Again, with the direct substitution method, you simply plug c in, and then you get c, whatever that number is, to the power of n. Again, this is how we find any y value. You take the given x value and you plug it into the function to find your y. And remember, the limit is the y value. Couple of other rules. Scalar multiple. Notice that if you're multiplying a function by some number, you can simply pull that number out to the front, find the limit, and then multiply it by that number. Product rule. If two functions are multiplying together, then you can split them up. Find each limit individually and then multiply those two limits together. Power rule. This is just like the one above. If some function is being raised to a power, simply plug your c value in everywhere you see an x in that function, get that number, and then raise it to the power of n. The sum and difference rule. If you have two functions being added together or subtracted, and you're trying to find the limit, you can split them up, find the limit separately, and then add or subtract those values together. Quotient rule. Again, notice you can split them up and find each value separately and then divide those numbers. This should be getting boring. Polynomials is a lot like the power rule. Again, simply plug your c value in for x, and everywhere you see an x in the equation, plug that number in and evaluate. Last one is radicals. It's slightly special. Again, same rule, direct substitution. You plug in your number everywhere you see an x. Here's the deal. Since it's a radical, you have to think about times when radicals can't be certain things. They're a domain. If n, the index, is even, this is an even, so a square root, a fourth root, an eighth root. Remember, you cannot have a negative number. So all your c values have to be greater than 0. If n is odd, so cubed root or a fifth root or a seventh root, then c can be any number at all. Let's practice a few of these rules. We're going to find the limits for the following problems. So 2a. Find the limit as x approaches 4 of 12 times the square root of x minus 3 over x minus 9. Again, are there any holes or vertical asymptotes at x equals 4? So if you plug this 4 in, will you get a 0 on the bottom? No. And does anything cancel when x equals 4? No. Thus it's continuous at x equals 4, and we can plug the number in directly. So the limit as x approaches 4 will be 12 times the square root of 4 minus 3 over 4 minus 9. Continue evaluating, and until you get your final answer, you must continue to write the limit as x approaches 4. This will be 12 times the square root of 4 is 2 minus 3 over a negative 5. 2 minus 3 is negative 1. Negative 1 times 12 is negative 12. So negative 12 over negative 5. Two negatives become a positive. So the limit as x approaches 4 for this particular problem is 12 over 5. So the y value you are approaching, the y value you're approaching as x gets closer and closer to 4 is 12 over 5. Let's look at the next example. The limit as x approaches negative 1 of x times x minus 4. All right? The domain of absolute values are all real numbers, so you're not going to get any holes or vertical asymptotes. Thus, you may directly plug your negative 1 in. So the limit as x approaches negative 1 is negative 1 times the absolute value of negative 1 minus 4. Evaluate this problem. You get negative 1 times the absolute value of negative 5. Remember that absolute values change everything from negative to positive. So we have the limit as x approaches negative 1 of negative 1 times a positive 5. And negative 1 times 5 is, of course, a negative 5. So our limit as x approaches negative 1 for this particular problem is negative 5. I want you to try this third example on your own. I will give you the final product, the final answer. You solve it yourself. So the limit as x approaches 4 for this particular problem is 2. Going to move on to the next page. We will be talking about theorem 1.5, the limit of composite functions. Remember that composite functions are what you get when one function is plugged into another function. So, notice that here you can find the limit of f of, like on the inside, you find the limit as x approaches c of the inner function, notice the inner function, and then you take whatever number that is, and you find the limit as x approaches the new number for the outside function. This makes more sense when we actually do an example, so let's get started. If f of x equals x plus 7 and g of x equals x squared, then find the limit as x approaches negative 3 of f of x. We're going to start here. To do this, we need to find the limit as x approaches negative 3 of x plus 7, because that is what f of x equals, x plus 7. As plugging in this number will give us neither a whole or a vertical asymptote, it's allowed. So I'm going to directly substitute it in and have negative 3 plus 7, which equals 4. So the limit as x approaches negative 3 of f of x equals 4. Let's try this. Let's go on to part B. The limit as x approaches 4 of g of x. This is the same thing as the limit as x approaches 4 of x squared, because that's what g of x equaled. It told us in the original problem. As this will create no holes or vertical asymptotes when we plug it in, I will do so immediately, and I get 4 squared, which equals 16. There's a reason I split this up into one limit and then another. Do notice that the limit here was 4, and then I took this 4 and I made it my c value for my second limit. Because now I want you to find the limit as x approaches negative 3 of g of f of x. Here's the deal. You start with the inside. What is the limit as x approaches negative 3 of f of x? So we start from the middle. The limit as x approaches negative 3 of f of x. Hey, we know that. We found it in part A. We know that equals 4. So that's what the inside is. So now they want to know, all right, well now find the limit, the new number that we have, the limit as x approaches negative 3 of g. And remember, we found out what this equaled, so what can we replace it with? A 4, because we know that's what it equals, which is going to be the limit as x approaches negative 3 of 4 squared. Because what was g of x? G of x was g of x equaled x squared, and that means we're going to have to plug this 4 in everywhere we see an x, so we do so. And then what does that equal? 16. This is just like what you used to do in Algebra 2. So, if they give you a composite function, simply find the limit of the inside using the number they give you, and then plug that new number directly into this outside equation. You simply have to write this to continue making it calculus instead of Algebra 2.